Let's discuss about phenols. This one is alternatively phenol is called carbolic acid. If you have two OH adjacent to each other, that is called catechol. If they are meta to each other, resorcinol. If they are para to each other, we call it as quinol or hydroquinol.
Okay.
In case if you have a CH3 instead of OH, it is called cresol. And if it is adjacent to each other, that means it is ortho to each other, it is called orthocresol, then metacresol, then paracresol. If all OH groups are adjacent to each other and three of them are there, that means it is called pyrogalol. If aldehyde is there, it is called salicylaldehyde. And there is nothing like O salicylaldehyde or M salicylaldehyde. Generally, salicylaldehyde by default is ortho position.
Mm.
Then salicylic acid. And if this oxygen's hydrogen is been replaced by acetate group, okay, so then this is acetyl benzoic acid, correct? This is
Yeah.
benzoic acid with an acetyl group. Clear? So usually we write it as acetyl O, acetyl O benzoic
Mm.
acid. Got it? That is called
So
as aspirin. This is
the
acetyl,
salicylic
right?
acid is
CH3C double bond. Hmm? And
yeah.
then there is oxygen connected to it. So that's why it can call it as O. Or
Okay.
you can simply call it as acetyl oxy benzoic acid. Okay. It
Okay.
is at ortho position, so you can write it as ortho acetyl oxy benzoic acid. That is the name. But the common name is more used aspirin. If instead of this OH group, if at all I replace with a phenoxy group, hmm, then what will this become? This is phenyl salicylic acid, correct? This entire thing is salicylic acid, but now we have
Okay.
phenyl salicylic acid, or we call it as phenyl salicylate because it is not acid anymore, it is a salt, so we call
Yeah.
it as phenyl salicylate. So phenyl salicylate is salol. The common name is salol. Salol is an antiseptic, which we use it as Savlon or Dettol or so on, right? So those are all salol forms. Next, if we have methyl salicylate, this is methyl salicylate. Methyl salicylate is called as oil of wintergreen. Okay,
Mm.
oil of wintergreen is usually referred because of its soothing on what do you say, heat. I mean, it will produce heat on the surface of the body. That's what it happens with move, Volini, Jendu balm, release spray, all
Ah,
of these. These all will have methyl salicylate. Got it?
yeah.
Next, how do we prepare phenols? Okay, these are very quick reactions. We'll go through it once. Check. Benzene, if you oxidize in the presence of vanadium pentoxide, but restrict the temperature to 300 degrees, then you get phenol. If you go beyond 450 degrees, the bond will break here and it will become this anhydrate, and that is called maleic anhydrate. Okay.
Mm.
Next, Dow's process. If you have a chlorobenzene react with NaOH, but it should be fused. Fused means there should not be any water content in it. Okay. So
Okay.
only fused form. Then in the fused form, if you attack, the Cl will go, you will get O minus Na plus, and that later on, if you hydrolyze, it will convert into phenol. Okay. The mechanism happens is through this one, where the OH minus will take H plus, removes chlorine, you will get a benzene. Can you see this benzene? A benzene is a pi bond outside the benzene ring, correct? This is an intermediate. Again, on that intermediate, OH minus will attack, O minus will come, that O minus will internally take H plus, you will get phenoxide ion. Okay.
Yeah.
This is called benzene mechanism. So this happens through benzene mechanism. Okay.
Mm.
Next. Next one is through benzene diazonium salt. This is benzene, N2 plus is diazonium chloride, BDC. Wherever you use this wording, which means we are talking about benzene diazonium chloride. And that when you boil with water, N2 will go away, water will come here. So it is simply SN1 type of reaction. Because SN1 is happening on an aromatic ring, you call it as ARSN1.
Yeah.
Okay, so it is called ARSN1 reaction. So
Mm.
water will attack here, you will get benzene, phenol form. Benzene sulfonic acid. See, sulfonic acid, when you react with fused NaOH, same via benzene mechanism, this O minus Na plus will attach here because first acid base will happen, H plus will be gone, SO3 minus will be present. And when OH minus will attack, this group will go out as SO3 2 minus. and you will get this fused form of O minus Na plus, and this, when you hydrolyze, will convert into phenol. Now, if there is a functional group, and on the functional group itself you are making an attachment, you are making a substitution, then that is called as ipso substitution. A substitution on a functional group itself is called ipso. Okay.
Mm.
If you have it on the adjacent carbon, you call it as ortho substitution, meta
Yeah.
substitution, para substitution. Now this is called ipso substitution. So you got an idea what exactly those are,
Yes, sir.
right? Next, cumene hydrogen peroxide. Okay. Honestly, mechanism is not essential, but I have given you in case if you want to refer. Okay. So check out what you have to remember here. See, if benzene is been using EAS reaction, electrophilic aromatic substitution reaction, with an alkene, which is propene, then pi bond will take H plus because I require a Lewis acid. So Lewis acid is H plus here. You will generate a carbocation and benzene will attack on this electrophile, and that's how you'll get cumene, right? You will be producing cumene. This is cumene. Cumene, when you oxidize them in air, in the presence of light, if you oxidize, between this carbon hydrogen bond, there will be an insertion of oxygen. Got it? That will, on insertion of this oxygen, you see this oxygen oxygen bonds are weaker. Any peroxy bond is very weak. Okay. In the light, this bond will break, and from here, this bond will break, phenyl bond will break, and that will connect onto this oxygen. So ending up phenol, and this part will convert into acetone. Okay.
Yeah.
Right. So again, mechanism is just for your reference. Don't worry about that. So final products are phenol and acetone. Okay.
Okay.
Next, the same reaction can be done with different migrating aptitudes. You remember that if you have hydrogen, phenyl, 3 degree, 2 degree, 1 degree, this is the migrating aptitude. Hydrogen will have the highest. Then phenyl with electron donating group, only phenyl, phenyl with electron withdrawing group. Then 3 degree, 2 degree, 1 degree, and methyl. Okay. Now notice here, when you react with O2 in the presence of light here, so you would notice that between this carbon hydrogen bond, O and O will get attached. Like this, you will get O and H, correct? Now
Yeah.
you have to decide whether methyl will migrate, phenyl will migrate, or a phenyl with methyl will migrate. So obviously methyl is a donating group here. So this has more chances to migrate. Okay. Does that make sense? Right.
Yes,
You're
sir.
deciding between these three groups. So which one will migrate? This one will migrate. So the one which migrates will convert into phenol. The other part will convert into ketone. So you will get this acetophenone, and this part will become phenols. Okay. So this is methyl substituted phenol. Next.
Yeah.
Acha, what do we call this methyl substituted phenol? You call it as cresol. So which position it is?
Yeah. Yeah.
Para. So para
Uh,
cresol. Okay. Next. Same here. This is a withdrawing group. NO2 is withdrawing group. So phenyl is there, methyl is there. So which one is migrate, beta? Phenyl will migrate in this case. Okay. So
yeah.
phenyl will form the phenol group. Rest of them will convert into the keto group. Okay.
Yeah.
Darkin's reaction is not there for JEE mains. Okay. It is only for advanced. But I'll just give you an idea what is to be done. If by chance there is a benzaldehyde, okay, and here between carbon and hydrogen also, you will get a peroxy linkage if you react with H2O2. Okay. And then you have to migrate this group. Phenyl has to be migrated. Okay. Now the phenyl migration depends on, correct, whether you have Z groups which are strongly withdrawing, strongly donating group. So you need to have a strongly donating group like OH, OMe, and NH2. Then only these reactions will take place. Okay. So
Okay.
as this group migrates here, then you will get this as keto form. So first you will get an ester intermediate. And after that, OH minus will attack, this bond will break. Eventually, you will get this form into phenol. The other part will become acid. Okay.
Okay.
Hmm. Next.
So,
Hmm.
so can I please quickly use the washroom and come?
Sure. See, the next reaction, the next preparation reaction is from salicylic acid. Okay. Now, Salicylic acid will have COH. You can remove COH by using simply soda lime decarboxylation,
Yeah.
isn't it? So you do that, remove carbon dioxide, you will get H. Okay. Now let
Mm.
me remind you, this is also a COH which is functional group, and you're removing that and putting hydrogen. So this is also an ipso substitution. Okay. This is also ipso substitution reaction. Done.
Yeah.
Next, if you have toluene, if you oxidize that in air or in the presence of copper salts or manganese salts, you will get this into a phenol form, and carbon will come out as carbon dioxide here. Okay. Again, no mechanism required. Same way, benzene, when you react with FeSO4 in peroxide, FeSO4 in peroxide is called as Fenton's reagent. That is called Fenton's reagent. Fenton's reagent, using a radical form, will convert this into a phenol. Okay. The byproducts of Fenton's reagent being these two phenols terminating with each other because they are radical forms. So you'll get a biphenyl as a byproduct here. Okay. Next, Grignard's reagent. If you have a phenyl magnesium bromide, if you react with oxygen, see, in the presence of oxygen, this carbon is having minus charge, right? Because Grignard's reagent, you'll always have this as delta minus and this is delta positive. So
Yeah.
that minus will attack on oxygen, make it into OO minus, right? And that O minus will again combine with MgBr. So it creates a peroxy linkage which is unstable. So if I take the second mole of this one, where you have delta minus here and delta plus here. So from here it will attack on this oxygen, break the bond onto this side. Okay? And that's how you'll get 2 moles of phenoxide ions now. 2 moles of phenoxide ions. That on hydrolysis will give you phenol. Done?
Okay.
Next, ELBS oxidation is removed from both JE and JE mains and advanced. It was earlier used to be in the old NCRT. Now it's not there, so let's not worry about it. Mechanism wise, let's not worry. But by chance, if it is given like this, phenol, if you react with S2OA 2 minus, it will
Mm.
give you quinols. Simple. Of course, there has to be hydrolysis followed. You will get OH phenol will convert into quinol. Okay, it's mainly for quinol preparation. That same logic can be applied even on beta naphthol. This is beta naphthol, this is alpha naphthol. Okay, and beta naphthol you will get at ortho position, at alpha naphthol we'll get it at para position. So these are the products you will have. Okay.
Okay.
Right, these are just like naphtha. This is called naphtha quinol, this is also naphtha quinol, this is ortho naphtha quinol, this is para naphtha quinol. Okay.
Yeah.
Usually, what are the terms you should know? Phenols are colorless solids. It has a typical phenolic order. uh, It is less soluble in water. It is only giving 83 grams per liter, and it is soluble in organic solvents. It is soluble in NaOH, reason being the pK value. Phenols are acidic in nature. So OH minus can take away H plus, converts into phenoxide ion, and that's how you will get water. And you know that water has a lesser acidic nature compared to phenol. And you know that in a acid base reaction, a stronger acid can give a weaker acid, but a weaker acid will not produce a stronger acid. So backward reaction is not feasible. Okay.
Okay.
The same logic I can say it is insoluble in sodium bicarbonate. Okay. Reason being, if you react with sodium bicarbonate here, so if I take phenol, sorry, first let me write down that word. Okay. Insoluble in sodium bicarbonate solution. Why is that so? See, if you have phenol plus HCO3 minus, then we are supposed to get pH O minus plus H2CO3. Now, if you compare the pK value, this is around 10, this is around 6. So, will it give? So, this reaction is not feasible. Done.
Yeah.
And this acidic nature can be used to make different acid base reactions. See, phenol, which has pK value around 10, with OH minus, it will take H plus away. You will get a phenoxide ion and water. This is feasible. With NH2 minus also, it can take H plus away, converts into ammonia. Ammonia's pK value is 38. So this is highly feasible.
Yeah.
With sodium, it can give electrons to hydrogen, converts into H2 gas. H2 gas also pK value is 38. So this is also highly feasible.
Yeah.
With chlorine, you cannot get HCl because it is -7. So chance ही नहीं.
Not
So
feasible.
RLi, R minus can take H plus, convert into alkane. Alkane has a very high pK value, so highly feasible. Okay.
Yeah.
Carboxylate, RCO minus to get RCOH, not feasible at all. H minus trying to give H2, definitely highly feasible. CO3 2 minus taking H plus, converting into sodium bicarbonate, which is 10.3 pK, this is feasible. But bicarbonate reaction, this is not feasible. No?
Yeah.
Now, if you compare the reactivity on base of phenols on with different groups on it, suppose I have a methyl, NO2 and cyanide. The electron withdrawing groups will always increase the acidic character. Electron donating groups will decrease the acidic character. And you know that NO2 is very strongly withdrawing. So therefore, this C will have more acidic nature than D, then A, then B. Correct? So C, D, A, B. That should be the order of acidic strength. Done?
Yeah.
Second case. If NO2 is present at ortho, meta, and para position, hmm, you notice that at ortho position, you have NO2, which is withdrawing. It is strongly withdrawing by minus I and minus R, minus I and minus R. And para also you will have minus M and minus R. And you will have minus I at meta position. Okay. It is extremely strongly withdrawing at meta ortho position. But problem here is at ortho position, it will also show a hydrogen bonding, intra H bonding like this. H, we have N, O minus, double bond O with plus. So you can see this is a bonding which has, okay. Due to this intra H bonding, which we call it as a chelation, its acidic
Mm.
strength slightly decreases because it takes little efforts to remove that H plus away. Okay.
Yeah.
Although NO2 is a very strongly withdrawing group, okay, because of this H here, so it will have slightly withdrawing nature here. That is part of chelation. Understood? That's
Yes,
why
sir.
in this case, slight exception is observed that para will be slightly more than ortho than meta. Okay.
Yes, sir.
Now, this is an important part to understand that when you have a two or three or more than three, two, three or more than three nitro groups on phenol, okay, then it will start giving a positive bicarbonate test. Okay. Just to
Okay.
show it as an example, notice this. Phenol with one nitro group, its pK value is around 8.9. Phenol with two nitro groups, its pK value directly goes to 4. And phenol with three nitro groups, its pK value is 1, which makes it very strong acid. And this is called
Yeah.
picric acid. This is called picric acid. Understood? So now tell me, if at all I use bicarbonate and react with this one, you're expecting to get H2CO3, whose pK value is around 6. This is 8.9 and this is 6. Is it feasible? No. But second, this is 4 and this is 6. I mean, this is around 6 here. Okay. So is it feasible? Yes, definitely feasible, because 4 to 6 it is definitely feasible. Now, here, this is also giving H2CO3, which is 6, and this is 1. Is it feasible? Yes, definitely feasible. That's why I said, if you have more than 2, now, it is not necessary it has to be at a certain position, like both ortho, one ortho meta, ortho para, nothing. Any positions. Even if you have 2 at meta positions, then also it will give a positive bicarbonate test. Okay.
Mm.
Okay. Next, when it comes to phenol, it has a certain dipole moment existing because of oxygen and carbon having strong electronegative difference. Okay. But here, because of OH and OH here, they should cancel off, correct? Isn't it? But they don't cancel off because there are lone pairs also on it, correct? Because of that lone pair, one, they will not be exactly opposite to each other. One dipole will be here, one dipole will be here, and this dipole will get added, and a resultant dipole will be in this direction.
Mm.
And that's why for quinols, dipole moment is non-zero. Okay. Clear? Next, see the reactions. There are two types of reactions, just we did it in alcohols. One is breaking of O and H bond, the other one is breaking of C and O bond. Hmm? So first let us see about alkylation. Same reactions what we did for alcohols. That is the same thing we are doing right now. Okay.
Mm.
So if you react with OH minus, it will take away H plus. You will get a phenoxide ion. Phenoxide ion immediately attacks on Rx, removing this X. So we get an ether form. Hmm? Clear, beta?
Yes, sir.
Okay. So this is that same Williamson ether synthesis. Okay.
Yeah.
What are the byproducts? See, when it comes to phenoxide ion will make a resonance stabilization also here, correct? And
Mm.
due to this, the negative charge which is forming here can actually attack on CH3Cl, and you will get this CH3 here. This is very similar to the Friedel-Crafts reaction. Well, if it is not exactly Friedel-Crafts, but it is very similar to that. Because in Friedel-Crafts, we use a Lewis acid. Here we are not using any Lewis acid, okay? Correct. So it is similar to. But here the attack is relatively less and ether formation is more. So this is a minor product. These two are minor products, while this is a major product, okay? Shana, clear beta?
Yes, sir.
Next, we see acylation. If you have OH and you use an anhydride formation, then the lone pair from here will attack here, bond breaking will take place, and you'll get OC double bond OR. Okay, same way. But for this to happen, usually basic medium is the best one. So either you use an OH minus or you use a pyridine. So pyridine can take away this H plus, or OH minus can take away H plus, creates O minus. O minus is a nucleophile, attacks here, breaks this bond. Okay. Same thing happens here also. OH minus will take H plus, O minus will form, O minus will attack here, remove out this Cl. So that's how you will get this product. Okay.
Mm.
If you are reacting that with acyl chloride in the presence of NaOH, then this is called Schotten-Baumann reaction. This name reaction is important. So in case if it is been asked, so remember what exactly Schotten-Baumann reaction. Okay.
Okay.
Next. Phenols can directly react with MeSO4 in the presence of acidic medium here. Sorry, basic medium here. So OH minus. So it will eat away H plus. O minus can attack on methyl. You'll get anisols. These are anisols. Methoxy
Yeah.
benzene is called anisole. The same logic happens with diazomethane. This is diazomethane. This will attack here. First CH2 minus will take H plus away, convert into this form. N2 is a good leaving group. Phenoxide will attack. N2 will leave. Again, you will get anisole. Okay. Next. Okay. This reaction is for the other case. I'll come back to that. Okay. Hmm.
Okay.
Now let's see the reactions where CO bond is involved. Okay. If you use zinc dust, zinc is an electron provider. So it will provide two electrons at this position, removing out this OH minus, and those electrons will take away H plus, converts into benzene. And you notice that this is a functional group on which you are removing and substituting an hydrogen here. So what is this one? Again an ipso substitution. So ZNO will be formed and benzene is the product. Okay.
Yeah.
Ammonia, when you react with Al2O3, ammonia can attack on this position, remove out this OH. Correct. This type of a mechanism we have learned it in aryl halides,
Yeah.
right? So where the attack would happen, the pi bond will shift temporarily. You will get a complex, MH complex, I told you, Mesenheimer complex. And thereafter, OH minus will be relieved out, correct? So this type of mechanism is called ARSN2. So from phenol, you'll be able to prepare anilines. Okay.
Okay.
This is a very standard sequence of reaction that you should remember from phenols beta. Okay. Let me quickly revise that. See, if at all I start with benzene, make H2SO4 reaction, concentrated H2SO4 reaction. Okay, sulfonation will take place. NaOH in a fused form will make a phenoxide ion, ipso substitution. Then on hydrolysis, we'll get phenol. Phenol with zinc and heat, again I'll get benzene. Just now we
Yeah.
learned. That on
Yes.
reaction with concentrated HNO3 will get nitrobenzene.
Right.
Nitrobenzene, when you react with tin and HCl, you'll get aniline.
Hmm.
Okay. Aniline, when you react with HNO2, will convert into a diazonium salt. Okay.
Right.
This step is very, very crucial. Okay. Every time it is added in the reactions. Okay. Aniline with HNO2 is always going to give
Hmm.
you diazonium salt. Diazonium salt, when you react with cuprous chloride, this is called Sandmeyer's reaction. That is what I'll explain you all now. Okay. This will remove this N2 and replace that with chlorine. So you'll get chlorobenzene. Chlorobenzene,
Right.
again, you use NaOH fused form. Just now we learned this is an benzyne mechanism. You'll get phenoxide ion. That on hydrolysis will give you phenol. Phenol with zinc will always give you benzene. Done. Very,
Okay.
very important sequence how they make these reactions. Okay.
Yeah.
This particular reaction, this is called Sandmeyer's reaction. Sandmeyer's reaction. Okay. Hmm. Right. Now let's see what are the EAS reactions of phenol. Okay. Phenol, when you react with bromine in CS2 or CCl4, here Br plus is not directly available, isn't it? Because it is a non-polar
Hmm.
solvent, it cannot create these ions. Okay.
Yeah.
Therefore, bromine can act like a nucleophile having an empty d orbital. Okay. But it
Hmm.
does not have exclusively Br plus available for immediate attack at all positions. So that's why this time when you have it in the weak non-polar solvents, bromination only either happens at ortho position or para position. In fact, usually para is always major. Okay.
Yeah.
But if at all you have bromine in water, aqueous solution, you will have sufficient amount of Br plus. So therefore, since now it becomes a Br rich solution, attacks happen simultaneously from all the positions, all ortho and para positions. Okay.
Hmm.
Thus giving you 2,4,6 tribromophenol. This is called 2,4,6 tribromophenol, which is a white PPT. Okay. Similarly, if there is a paramethyl phenol, then on bromination, we'll get Br and Br at two ortho positions. Clear?
Yes, sir.
Right. Next, if you have a phenol with COH or SO3H, okay. Now, when you react with bromine water, this COOH or SO3H will be shredded off. This will be shredded off to get an ipso substitution first. This we have done it earlier. Okay. So that
Yeah.
removing out COOH, you will get first hydrogen. Okay. And thereafter, once your COH is gone, HS come and again bromination will happen. So that's how you'll get 2,4,6 tribromophenol.
Sir, what do you
Hmm.
mean when you say shredded off? Like, is that a...
Ipso substitution, beta. That means it is
Acha,
ipso
okay.
substitution. That is CO2 is removed out, hydrogen is been attached.
Okay,
Okay.
okay. I thought it meant something else.
No, 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 no. Just I'm using it as a crude way to understand. That's it. Okay.
Acha, okay,
You
okay.
remove CO2, push H plus here,
Yeah.
and thereafter, once you get H plus, again you do bromination, you'll get this form. Okay.
Okay.
Even if it is present on ortho position or and para position, both the reactions will be same. Hmm?
Hmm.
Next. This was once asked that if you take phenol with NaOH and bromine, of course, in NaOH and bromine also you'll have sufficient Br plus. So you will get 2,4,6 substitution. Okay. The question what was asked in JEE Advanced was out of these following, which of them are possible intermediates? Okay, out of these are which are
Yeah.
possible intermediates. So basically, it is emphasizing on mechanism.
Hmm.
Now, notice the mechanism here. First, OH minus will take away H plus. You will get phenoxide ion. Correct. Phenoxide ion can push here. This pi bond can push here. From here, bromine can be attached. So you will get this is the first intermediate. Hmm? You got this intermediate beta,
Yes, sir.
right? Thereafter, to retain the aromaticity, OH minus can attack on H plus, push here, and O minus will come. So what did we get? You get aromatic ring again. So this is one of the products you can get, correct? Now
Yes,
this
sir.
can go further. This can go further reaction. Now again, if you have Br and Br here, so this can push, pi can attack, Br minus will leave. So what do I get again? I will get double bond O, double bond Br here, and Br and H here, correct? Again, OH minus can push, take away H plus. This will push, O minus will come. So I will get O minus, double bond with Br and Br, okay?
Mm.
And the same can happen on this side also, no? So this, right? These are all different forms of intermediates, correct?
Yeah.
And if you notice that, this one definitely is a possible case. This two bromines at the same position, impossible, right? This is not possible.
Right.
This one is a possible case. At meta position, it is impossible because it is
Mm.
an OP directing group. Although it is possible, this is also possible. Done?
Yeah.
Clear now?
Yes, sir.
Next. This is not essential. I'm skipping this, okay? It's not required. Next.
Okay.
Sulfonation. If you react with concentrated H2SO4, you will get either at ortho or para position. Usually, if you operate at a lower temperature, then major product is always ortho substituted. And this is called kinetically controlled reaction.
Mm.
Reason being, when you substitute sulfonation at ortho position, you will have here O and H with S double bond O, sorry, with SO minus, double bond O and double bond O, correct? This
Yeah.
intermediate will get stabilized by intramolecular hydrogen bonding. Hmm? Now, if you compare to this intermediate, which is at the para position, O and H with S, O minus, double bond O and double bond O. Now, between these two, which intermediate seems to be more stable? This one, right?
Right.
Now, a route where you have more stable intermediate is called kinetically controlled reaction. A route where more stable product is forming, that is called thermodynamically controlled reaction. Now you
Yeah.
can see at a lower temperature, this is major product as it is kinetically controlled now. Okay. While between these two products, if you notice, this product is actually more stable due to hydrogen bonding because hydrogen bonding can happen here as well as here.
Yeah.
So intermolecular hydrogen bonding is more, not intra, not within, but between two molecules, this would have more. So this is more thermodynamically controlled. And high temperature always famous thermodynamically favored. Low temperature always favor kinetically controlled product. Done?
Mm.
So very important to learn which is major in what case. Okay. But if you are pushing excess amount of H2SO4, then you will get only two SO3H. You will not get all three. Okay. Again, probably this is because of the bulkiness of SO3H. There is no particular reason to it, but remember it. What is given in NCRT, we will just simply follow that. Okay. The reason probably could be because there is no clear information given on that. So it is because of the bulkiness of SO3 and strong withdrawing nature. Probably the third SO3 is not coming in. Okay.
Okay.
Done. If you react with dilute HNO3, you will get only one nitro being substituted either at ortho or para. Okay.
Mm.
Right. There are two mechanisms proposed. That is one directly NO2 plus will come, and that is getting attached on ortho and para. Or HNO2 will always be present in the presence of HNO3 in a small amount. And that this HNO3 with HNO3, both of them reacting with each other, will generate NO plus and here, this is one more. Okay. It will generate NO plus and NO3 minus. Got it?
Mm.
And because of that, NO plus first attachment will happen and NO will further get oxidized in the presence of HNO3 to get nitro. Hmm, clear? Alternatively, we can also use NaNO2 in concentrated HCl. This will become NO plus. Okay. NO plus can be again substituted at ortho or para position. So you'll get NO, and then you add dilute HNO3, it will convert into this NO2. Now this reaction will make a better yield as compared to the first case. Okay. So that's why this is a better recommended reaction for getting single nitro group. Okay. But if you use concentrated HNO3, phenol will react, as per, in NCRT, this is mentioned that with concentrated HNO3, you will get ortho, para, substitution. All of them are getting substituted. Okay. But this product will not be major, beta. This will not be major. Okay. Because concentrated HNO3 is a strong oxidizing agent itself. So it will oxidize the phenol part into quinone. It will oxidize into quinone. Okay. So to avoid that quinone formation here, okay, so concentrated H2SO4 in excess amount, clear? First, you know that it will give SO3H. And once you do that, then you do concentrated HNO3. Now what happens? Because this is already a strong withdrawing group here, this oxidation of phenol will not take place here. Instead, only nitration will happen at one position first. It will happen at one position here first, SO3H, and SO3H will be present here beta first. And thereafter, if it gets further, because it is in a concentrated acid, it will get ipso substitution. That means here you will get hydrogen.
Yeah.
Right. And here you will get hydrogen. Now again you do nitration, so you will get two more NO2 groups. No? Thus converting into picric acid. Now this is a better yield. So instead of going to this route directly, you first do sulfonation followed by nitration. Okay.
Okay.
Next, if at all I have a phenol, aniline, quinol, or aminophenol, or like this two amino group benzene, any of these groups in the presence of oxygen, they all will get oxidized to only one form, which is quinol. Okay. In fact, even if you take phenol with, KMNO4 in basic medium or acidic medium and heat, these will also get oxidized into quinone. Quinone is a oxidized form of any kind of phenolic ring. Okay. Friedel-Crafts reactions, if you take alkyl halide in the presence of AlCl3, okay, you will see you will get at ortho position and para position. These two will get substituted, correct? But this is typically very low yield. This is a very low yield which you will get. Okay. The reason for that is the lone pair on OH will react with AlCl3 as an acid base reaction here and makes this as a withdrawing. That's why benzene ring is less activated in this case. Okay. Right. Now let's see all the name reactions at once. Okay. 1 second. I'll show you name reactions in another file. Right. Here. These are all the name reactions. You can see first, starting with Riemer-Tiemann reaction. Okay. Riemer-Tiemann reaction is when you have a phenol react with, chloroform in the presence of NaOH, and after that the second step is hydrolysis. See the mechanism here. The mechanism is, usually asked in GE. So learn the mechanism thoroughly here. Okay. If you ask in phenols, the mechanism where you need to learn is this one. One is this one. The other one is the bromine water. Correct. Only these two positions you have to, at these two reactions, you have to learn mechanism. Okay, beta. OH minus will take H plus from here, convert into CCl3 minus. It is like an acid base reaction. CCl3 minus is this kind of structure, a pyramidal structure. Carbon with a lone pair and three chlorines on a plane like this. Okay. Shana clear beta?
Yes, sir.
Now these three chlorines, on the same plane will repel each other. their electron densities will repel each other. That gives away Cl minus and converts into CCl2. So this CCl2 which is forming, which you call it as dichlorocarbon, is an electrophile. It has an empty orbital. And you have generated empty orbital and kept it. Now coming back to the phenol. Phenol OH, in the presence of OH minus, it will take H plus and it will become phenoxide ion. The reason to use NaOH is two purposes. One, to generate this electrophile. Second, to activate the ring, because phenol will get further activated if it become phenoxide ion. Okay, very strongly activated. So this is a very strongly activated ring. And then O minus will push electrons. Pi bond will attack on CCl2. Okay, and CCl2 will become CCl2 minus. That minus internally can take H plus to restore the aromaticity. Thereafter, O minus will push it into a double bond. The double bond will keep pushing outside so that the chlorines can be removed out. So one chlorine is out. As one chlorine is out, the basic group can attack as a nucleophile. Pi bond could regain the aromaticity and again it becomes O minus. This keeps on happening till all the chlorines will leave out. So you can see O minus will push, again pi bond will push, Cl minus is gone. And
Yeah.
when that happens, now the base group will take H plus from here, creates O minus. O minus will make a double bond, regains aromaticity, and finally you will get phenoxide ion. Okay. Now this phenoxide can take, H plus. Sorry, here there is no H here. I'll just remove that. Okay, this way. Okay, and thereafter on hydrolysis here, you can see on hydrolysis, we can convert that into a salicylaldehyde. Okay, clear? Now you might wonder the same thing, sir. We can, because the attack is happening on ortho. Why can't it happen from the para position? It does, but that is not major. It is minor product. See, reason why it is minor is when you are using NaOH, because I'm using NaOH here, correct? NaOH, the sodium size is appropriate to make a nice ring formation here. Okay, so which will stabilize the intermediate momentarily. When the electrophilic substitution happens, it will stabilize that group momentarily. Okay, this is called chelation. Okay, due to this chelation, it will become very stable. Understood?
Okay.
So instead of going at para position more often, it will uh, exhibit stability on the ortho position. That's why salicylaldehyde is a major product here. So this is a major product. If at all I use NaOH, but by chance I use KOH, right? It will go for para position. So now because K plus is sufficiently big in size, so it will not be able to give the better chelation. Okay. This is Riemann-Tiemann reaction. Now, if ortho is already being occupied by some group, like OM is already occupying that group. Okay. In that case, because ortho is not possible, although here it is possible, but that will always try to make chelation. The sodium can make a chelation here itself and avoid making chelation here. So that's why instead of going an ortho position, now it will definitely go at para position. Okay. So major now will be para, minor will be this one, ortho. Okay. This was once asked in JEE Advanced. I mean, very old question, wherein if I want to prove the evidence of dichloro forming as an intermediate, okay, or as an electrophile dichlorocarbon is forming, you take a paracresol, react with this CHCl3 and NaOH. Now you will get salicylaldehyde here, which is major, but at the same time, there is a sufficient amount of minor product which is unexpected observed. That is, at this position, there was an electrophile CCl2 which was added up, and that CCl2 will take H plus from the hydrogen here and convert that into CHCl2. So this was a product which was observed. Okay. So this product was the confirmation that of course there is a CCl2 which is an electrophile through which this reaction is happening, and finally we are getting a salicylaldehyde. Okay. Now notice Remer-Tiemann carboxylation. So that means instead of aldehyde, now you are making a acid group. For that, you
Mm.
don't take chloroform, you will take CCl4 directly. Hmm? NaOH is taken to remove H plus, phenoxide ion is formed. The pi bond will attack on carbon, remove one chlorine from here, so you'll get CCl3. Okay. And when you react with OH minus, all the chlorides will keep removing out with OH minus, and finally they will convert into COO minus. And this on hydrolysis eventually becomes salicylic acid. Okay.
Yeah.
Next, this is an abnormal case of Remer-Tiemann reaction. This is called abnormal Remer-Tiemann reaction.
Mm.
Instead of benzene, I'm taking a pyrrole because this is also an aromatic group. Hmm? So this
Yeah.
should also give you EAS reactions, and this should also give you aldehyde here. So which you will get, but this is not major. The major product is this beta chloropyridine. This beta chloropyridine. Why that is happening here? See, pyrrole, when it tries to attack on CCl2 beta, when it attacks on CCl2, CCl2 will attack back here to make an addition reaction. You might say, sir, the same thing should have happened in benzene also. Well, in benzene, substitution is always more favorable because its aromatic nature is quite high. Okay. So, but here addition could happen because in addition, the adjacent groups will help it to get resonance stabilized again. Okay. So once you get this three-membered ring, the lone pair on nitrogen will push this three-membered ring will break to remove this chlorine out, and you will get this compound. And OH minus will take away H plus, and that's how you'll get beta chloropyridine. Okay. So
Okay.
instead of getting this one, which is a Remer-Tiemann reaction, now you are getting this one also, which is abnormal Remer-Tiemann. Okay.
Mm.
Next one is Kolbe-Schmidt reaction. This is another way of generating salicylic acid. That is, if you take phenol, react with carbon dioxide and NaOH. Okay. Here, carbon dioxide is directly taken as electrophile, but it require a highly activated ring. That's why we are taking NaOH. So NaOH will take H plus away. The phenoxide ion will attack on carbon dioxide. And I told you that if at all I take NaOH, it will give better chelation on the ortho position. So you will get this as the intermediate. And thereafter, OH minus will take H plus away, retain the aromaticity, and that's how you'll get salicylic acid. Okay, correct. If at all I take NaOH, ortho product. If at all I take KOH, para product major. Okay. Hmm. Aspirin. Now these three reactions are very important, very simple ones. See, this is an check out. This is an salicylic acid. If at all I use an anhydride in the presence of pyridine, yeah, notice anhydride will make an esterification with OH group, correct? Because alcohol and acidic group will always make an ester.
Mm.
So think like an esterification. So remove OH from here and this acid from here. You will get CH3C double bond O that will get connected to form ester. So this is an ester and this is an acid. That is called aspirin. Hmm. Second, methyl salicylate. Now this time you are taking alcohol here and acid is here. Between these two, esterification will happen. So ester will form here. Okay. So now this is an ester with an hydroxy group. So this is a pain balm, or also known as oil of wintergreen. Same logic, instead of methanol, if at all I take phenol, again you remove OH from here, H from here, you will get an ester. This is salol, which is an antiseptic. Okay, very simple preparation, but it is uh, quite a very frequent question that is asked. Okay. For aspirin, there are three important points you should know. One, it is analgesic, which means it is painkiller. Next, it is antipyretic. Antipyretic means which will reduce the temperature. Third, it is used as an anti-blood clotting agent. Got it?
Yeah.
Next, phenolphthalein. Only the reaction is important, so just notice that phenolphthalein reaction. If I take 2 moles of phenol, react with a phthalic anhydride. This is phthalic anhydride. Okay.
Mm.
Phthalic anhydride. Okay. And this is phenol. Correct. So when you mix these two, phenol and phthalic anhydride, you will get phenolphthalein. Basically, you are making two EAS reactions back to back. Hmm?
Yeah.
How it works? See, in phthalic acid, phthalic anhydride, if you put it in acidic medium, this lone pair will take H plus, thus making this carbon to have sufficient positive charge. And that's when phenol from para position will attack here and convert this into OH group with a phenol. Okay. And since you are keeping it in acidic medium, this OH will take another H plus, becomes a OH2, which is a leaving group, and that
Mm.
makes it carbocation again. Now the second mole from the para position will again attack. So that's how you will get this phenolphthalein. Very easy. So you just need to understand there are two EA steps happening. Okay.
Yeah.
This was also a question which once asked, that how the color is forming in phenolphthalein, right? See, when you add base, that means you are increasing the pH of the solution. And you know that phenolphthalein is used as an indicator which has
Yeah.
range of 8.5 to 10.5. Okay, 8.2 to 10 basically, but that is the range. Okay. So in that range, which means as you start increasing the basic medium, it will start becoming more and more pink. Correct? Why that happens? See, in the basic medium, OH minus will take H plus from here, converts into this O minus form. Hmm? And this O minus form, as it pushes here, it will become a quinoid form. This is called quinoid form. This type of a form is also benzenoid, because these are all benzene rings, right? These are called benzenoid form. Okay. And now this is becoming something like a quinone. So it is called quinoid form. Okay. If there is a conversion from benzenoid to quinoid, always there is a color observed.
Yeah.
So this is colorless form. This will become pink color. Done?
Yes.
Right, beta. Next, if you have an acetone reacting with 2 moles of phenol in concentrated H2SO4, same reaction just now like how we learned it. That is this way. If you have OH plus, correct, and phenol from para position will attack here. This will go. So you will get one phenolic group here like this. And then we have OH. And if I
Mm.
do protonation, again OH2 will go and second mole of phenol will attack. So here also two EAS reactions. Two EAS reactions will convert into this product, bisphenol acetone. Okay. BPA. Okay.
Yeah.
Next. This one is not there for you. Now come to this one. Lieberman nitroso test. Very important. This is a test used to detect the phenol group. Acha. Lieberman nitroso is used in two reactions, beta. One is to predict phenols. Okay. Second one is to predict is to predict the 2-degree amines. One is to predict phenols, second one is to predict 2-degree amines. Okay. So it is test used for both of them. So if the question is asked more related to phenol, okay, or if you see the options there are phenol, you can go for it. That is also showing Lieberman nitroso test. But if the
Okay.
question is more amine oriented and if it is given everything in terms of amines, that means there also Lieberman nitroso test is happening, but that is for only secondary amines. Okay.
Okay.
Notice, if I take phenol, treat with HNO2. See, HNO2 directly cannot be produced. That's why we take NaNO2 and HCl.
Yeah.
On doing so, we will get NO plus as the intermediate. I mean electrophile. So from the para position you'll attach, you'll get this NO. And nitroso can always undergo tautomerism and that can become oxime. So you can see
Yeah.
oxime. So this is a quinone based oxime. So that's why it is called quinone monooxime. And I told you from benzene, if at all anything changes to quinoid, color change will happen.
Right.
And that's why it will show green color first. Okay.
Mm.
And then in acidic medium, if you keep it in acidic medium here, you can see this OH can take H plus from here, becomes a good leaving group. That's where from para position, it can attack on nitrogen. Right. Again, a ES will happen. Now this time, the product which you will get here, this will still have a quinoid form. Can you see this is still having a quinoid form? And that will also show color. And this time the color is red. And the name is indophenol. And if I take NaOH, this OH minus will take away H plus, and it will become OH will become O minus, and still I have a quinoid form. Now this time the color is blue, correct? So this is called green, red, and blue color formation. GRB. Okay,
Yeah.
GRB publication books. You can remember it
Mm.
that way. Okay, so
Yeah.
GRB books. Okay, so yeah, Lieberman nitroso test is about GRB test. Okay,
Okay.
right. Next.
Uh, so,
Yes, but
can
one second.
let me stop here. I have a doctor's